Hi and welcome to this session. This is the second video in the series. We are discussing Monte Carlo simulation of a valuation model in Python and using xlwings. For those of you who have not yet watched the first part, let me quickly summarize what we did. We started with a valuation model I had, but there is really nothing particular about that specific model I am working on. You can do everything we do for your own model. In the model, we had several input variables and we assumed we are uncertain about only one of them, which was the growth rate of the addressable market. We assumed that this growth rate follows a normal distribution and we simulated our model using this uncertain input. As a result, we got the distribution of possible value per shares for the business. We also plotted the cumulative distribution function showing us the probability that the value per share falls below a specific threshold. I provide the link to that video in the description if you decided to go and watch it. In this session, we will do three things. First, we want to move beyond one uncertain input. We will see how we can add one extra uncertain input. If we learn this, then it would be straightforward to increase the number of inputs to 3, to 4, and more if needed. Second, we also want to add distribution plots for our input variables. This helps ourselves and others to understand what the uncertain input variables are and what we have assumed about their distribution by only looking at the outcome of the simulation that we will report in Excel. Finally, we would try to apply some formatting to our results in Excel so they look a bit nicer. While going through these steps, we will also clean up the codes we wrote in the previous part and we will try to make some parts of the codes more efficient. If you have the codes for part 1, you can start from those and try to adjust it for yourself as we go on. If you don't have those codes, no worries. You can follow me here for now, since I will start from an empty page, in fact. One important note to those of you who are beginners to Python programming: don't freak out if you cannot fully understand everything behind the structure of some codes we write. I am a big fan of learning by doing. It's too boring, honestly, to start reading all sorts of stuff. My philosophy of learning programming is to start doing projects that are useful and important for us, like what we are doing. We will slowly learn how things work, and if we really wanted to know more details about some specific things, then we can go and learn them after we see the need for learning them. This way is much more fun and we will learn it much better. It's kind of learning a language, I think, by practicing to talk. Okay, that's enough of the intro. Let's get started. Are you ready? Let's go. First, we always import necessary libraries. Here we need the followings. In particular, we need xlwings, and also from xlwings we import constants that we will be using for some formattings. We will also see how pandas is going to help us make the codes we wrote last time much more efficient. In addition, we will use matplotlib for plots, and we will learn how we can make the process of generating the plots and exporting them to Excel much more efficient than what we had before. We will also use numpy, and from numpy.random we import uniform since we will be using this distribution here. After importing the necessary libraries, we connect to the workbook where our model is located. If you remember from the intro to xlwings video, we use the object book to connect to a workbook, and we need to pass the name of the file. Here my Excel file is called DCF_model. I remind you that if the Excel model is not in the same folder as the codes, you have to provide the full path for the model. Also, we always need to provide the extension XLSX here. Okay, this is how we access our workbook, and let's call it book. Then we access the specific sheet within the book that includes our model. Here, the name of my worksheet is sheet 1, and I call it DCF_sheet to be able to access it. Finally, we can create a new sheet and we will name it simulation. So these are all we also had in the previous part. Now, before running our simulation, we always need to decide what our uncertain inputs are and what their distribution looks like. Last time we assumed that the growth of the addressable market for our company follows a normal distribution with the mean of 10% and standard deviation of 3%. Let's keep that assumption. In addition, I would like to add one more uncertain input here. Let's assume that we are also uncertain about the market share of the company in the terminal year, which is in fact market share in 10 years from now. The market share is also one of the inputs in this specific model. The current value we have entered as the input for market share is 30%, but we believe it could be anything in the range of 20% to 40%. Here we are going to assume that it follows a uniform distribution with the lower bound of 20% and upper bound of 40%. We can in fact quickly generate some data from such a distribution and plot it so we understand the differences between a normal and uniform distribution. We can use NumPy random function and generate data from a uniform distribution with these lower and upper bounds, which was 20% and 40%. We generate 1,000 draws from such a distribution and we call them a data. Now, let's have a histogram of such data with 10 bins, for example. It's clear from the plot that the draws are always between 20% and 40% with kind of similar likelihood. Still, it appears that some numbers are more likely than the others, but that's due to the limited number of draws we had. The more draws we have from a distribution, the more precise it gets. That's why in the previous session we saw that when the number of simulations are low, the outcome is strange and not reliable. For example, here if I had only 100 draws, the empirical distribution I observe indeed looks way different than the uniform distribution I was planning and hoping to have. But if I increase the number of draws to 10,000, it gets much more precise, as you can see. So that's the intuition on why we need to run our simulation at least several thousands of times to get proper outcomes. Now that we discussed about number of simulation, let's define it here and give it a number. Let's, like previous time, let's start with a very low number so we run the codes easily, and then we can increase the number of simulations to see the proper outcomes. Let's start with 100 simulations. By the way, you can also see the difference between uniform and normal distribution if I simply change uniform here to normal. Okay, as you see, There is no strict boundaries for a normal distribution, and also the probability of realizing the values in the middle of the range is the highest in a normal distribution. And as we go towards the sides, this likelihood gets lower and lower. In fact, there are many types of distributions we could in theory use for our input variables, but for now let's work with normal and uniform distributions, which are, by the way, among the most useful ones for us. In a separate video in this series, we will discuss the details about all useful distributions and which ones for which types of inputs we should be using. Okay, now I think we have all the main parameters for the simulation. I have decided the number of simulations. I know my uncertain inputs, which are the growth rates of the addressable market and the market share of the company in the future. I have also decided how the probability distribution of these uncertain inputs look like. With this, let's get into the Monte Carlo simulation. For those of you who watched the previous part on this series, you will realize that we will be simplifying the codes by getting some helps from pandas data frames here in particular. Now, first let's generate random draws for the growth rates, which we said should follow a normal distribution with a mean of G underline mean and standard deviation of G underline STD. So we draw a random growth rate out of this distribution and replace it to the corresponding cell in our Excel sheet for this input, which is the cell E2. Let's do the same process for our other uncertain input, which is the market share. We said that it follows a uniform distribution with the low bound of market share low and upper bound of market share high, both of which we defined above when setting the parameters for our simulation. They were 20% and 40%, and of course we can easily change them later on if we wanted. I also replaced this randomly drawn number into the corresponding cell value in Excel for this particular input, which is J3. Now that we generated new input variables and replaced them in the model, all we need is to locate the output cell of our model and get the value of it. Our main output here is the value per share, which is in cell B45, and let's call it price. As we discussed previously, since xlwings brings values that are in cells with accounting formats as decimal, we get the float of the price to have the regular format of the number. So this is one round of the simulation, if you wish. All we need to do now is to have a loop around this, and the loop will be running as many times as the number of simulations that we have decided. Let's move all these codes inside the loop by pressing the tab key. Now we need to collect the simulation results. Let's start with an empty cell before the loop starts and call it outcome. Then at the end of each round, let's append to this list the values we would like to have. Of course, we need the price, which is our main output, but I would like to have also the estimated growth rates and market shares for each round of simulation together with the price. So essentially, as the output, I am collecting here both the estimates of the uncertain inputs and the output that is generated by those inputs in each round. Okay, now let's put this outcome in a data frame and let's report the first 5 rows of the data frame to see what it gives us. These are obviously the 3 variables we collected. We can give an appropriate name to each column. Growth rates is the first one, market share is the second, and the last one is the value per share. So now, in fact, we can create a function around this. Let's call the function DCF underline simulation. Our simulation function would get as inputs a number of simulations, the mean and standard deviation of the normal distribution for our market growth rate. And finally, we need the lower bound and upper bound of the uniform distribution for the market share. At the end, we want the function to return our data frame that includes the growth rate, the market share, and the estimated value per share as a function of those. We also need to clear the simulation sheet each time that we run this function so that we do not mix the current numbers in there with the numbers from another simulation we will do again later on. Okay, now let's go back and increase the number of simulations to 5,000. Run our simulation function and wait till it finishes. You can see in the Excel file what the simulation is actually doing. It's assigning new values to the 2 uncertain inputs we have, which then feeds to the model in the Excel model and then generates a new value per share in each round, which we also ask the simulation to collect. It will take some time, so let's fast forward. Okay, well, all seems to be fine now. Of course, now I can easily change the parameters of my simulation and run it again and again if needed. Here, let's keep the setup and the results we have. And note that the output of our simulation is in fact the data frame including the estimates of the 2 input variables together with the estimated value per share. We can now easily copy this data frame in our Excel sheet. Remember that my simulation worksheet is called sim underline sheet. I have 3 columns in the data frame that I would like to copy in Excel. Now I want to have them in the first 3 columns starting from the cell A1. Since I do not want the index to be copied in Excel in the options, I set the index to false. So now if I run this, our data frame will be copied as the values of the cells in Excel. Let's run this. Now we see that the data frame we had is now in Excel exactly where we wanted to go. Now let's try to plot the outcomes in an informative way. Let's first define our variables so that we can easily refer to them later on. I create 3 variables referring to each of the columns in the data frame. The first one is growth rate, and I call it growth. The second one is market share, and I call it market underline share. And the third one is value per share, and I call it DCF underline value. I can also choose a plot style, and here I would like to use Seaborn, which I think produces nicely formatted plots. Now, let's create a new cell and start our codes for creating some nice plots. We start by naming our figure, which I call it sim underline fig, standing for simulation figure. We can assign figure size to it if we want. Let's say fig size equals 10 and 10. Of course, we will adjust this afterwards if needed so that the figure looks good. Now, what I would like to do is to create 4 subplots in this figure. One for the distribution of value per share, the second one for my cumulative distribution function, and the other 2 for the distribution of my 2 uncertain input variables. So now this is a great time to learn how to do subplots, at least one way to do them. Since I need 4 subplots, 2 by 2, I would write plt.subplot and then specify 2 by 2, and then the last argument is the position I want this specific subplot to go. I want to be in the first position, which means the top left subplot. So this is specifying the position of this current subplot I am going to have. And I want to have histogram of the DCF underline values here. I can define the bins, of course. I can also define the labels for my x and y axis. My y-axis would show the counts or frequency here, and the x-axis would be the value per share. I can also add a plot title, and let's call it a distribution of value per share. Okay, I can also increase the font size of the title so it's visible enough, but it's not too big either. Okay, sounds good. Now, I would like to also add a vertical line showing me where the average estimated value per share is in this histogram. Let's do this time a different and perhaps a nicer way by using plt.axvline, stands for vertical line, of course, and then DCF underline value dot mean. We can also label the line as average price, and let's have the color red for it. We also show the legend to be clear as what the line is reporting to us. Okay, so now this looks good for my first subplot. Now let's keep position 2 free for now at the moment, which is going to be the CDF plot, as we said. And we do the subplots for the input variables now. So I can copy these codes here and paste it twice. Again, this is 2 by 2 subplots, which means 4 subplots. And this specific one, let's put it in the third position, which means the bottom left position. The x-axis here shows the market growth rate, and the title is the distribution of market growth rate. Okay, so let's repeat this for the market share subplot as well. It's going to be in the fourth position, which is the bottom right subplot, and I change the axis titles and title of the subplot accordingly. Okay. Now I can also change the color of the bars for these input variables to another color, for example, green, to distinguish the plots for input variables versus those of the output variables, which will be listed in the first and second position. Okay, looks fine now, I think. Finally, let's fill the second position as well. Here I want to have the cumulative distribution function of value per shares. So the position of the subplot is 2. We discussed in the previous video that the cumulative distribution function helps us answer questions like what is the likelihood that price falls below a threshold? If you remember, the x values in a CDF plot are the sorted data, which in here means sorted value per share estimates, and the y values correspond to the proportion of data points less than each data point. That could be written this way. Okay? So if our x is $30, for example, our y would be the proportion of the value per share estimates that are below or equal to $30. This shows the likelihood that the price falls below $30 and is a very useful metric for understanding the downside risk we are facing when investing in a particular company, for example. Okay. Now, I plot the x and y, and I can assign a marker. Also, I don't want the dots to be connected, so assign a line style to be none. Finally, I adjust the labels and titles as well. Okay, all seems to be fine. And now, for the plots to look better, we can adjust the space between them by using W space, standing for width space, and H space, standing for height space. What this does is essentially adding white space between the subplots. Let's play around with it till it gets nice. Okay, now it's fine to me. If you are picky, you can spend more time on making them more beautiful, of course. Now we have all these subplots, but they are in fact 4 subplots inside one figure. So to import them in Excel, we only need to add the figure, and obviously it will copy all the subplots there, which is quite nice, I think. So let's define the location where we want to add the figure. I want to add it into simulation sheet and in range J2. In fact, I want the top left corner to be on this range, which I refer to it in the next line when I am adding the figure. Okay, so let's call this range R and G. And now I can access to simulation sheet pictures and add this new figure, which we defined it above with sim underline fig. We can also assign a name to this figure in Excel. Let's call it the same name. Okay, I set this figure to be updated, and we assign the top left range for the figure to be set on what we defined above, RNG top and left. Now, If we run this cell, it should add the plots to our Excel sheet. Let's do that. Okay, beautiful. Now, let's also add the descriptive stats for our simulation data. Since we have our data on a data frame, I can easily use the describe method to give me the descriptive stats. Okay. When I have that, I can also easily copy it into Excel in the simulation sheet and in whatever range I want. Let's send it to E2, run the cell. Okay, perfect. Now, I have all my simulation output data. I have the plots I needed, and I have the descriptive stats. One interesting thing we can always do in this kind of analysis is to inspect the relationship between our inputs and output variables. For example, it would be nice to see whether there is a linear or non-linear relationship between the growth rate of the addressable market and the value per share in this model. I can easily look at this by having a scatter plot of growth versus a DCF value. Here we could easily see the relationship, whether it's linear or non-linear, etc. We can, of course, do this for all our input variables. We could even get much deeper in these and also export them in Excel if we needed, but for now I want to move on to talk about formatting a bit. As you see, we have all our simulation outcomes exported in Excel exactly where we want it, but they are not presented in a nice format. Let's try to make them look a bit nicer. To do so, let's first define some ranges so that we can apply different parameters and formats to different ranges. For example, we typically have different formats for headers than the data itself, and so on. Here I would like to define several ranges, one for the output range, which is for the whole first 3 columns. We get this range by passing cell A1 but applying the option expand, and the default value for it is to obtain all the table. Expand to the right and to the down, in fact. We can also assign header range to be only the first row, and also data range, which is only the data excluding the header. Similarly, I define several ranges for my descriptive stats table. Here I have an additional range, which is the name range that I would like to apply a separate formatting to it. Okay, so depending on how many different formatted cells you would like to have, you can define separate ranges so you can apply specific formats to each one. And now that I have my ranges defined, I can start applying different formats to them. First, let's change the font and size of all our headers and text in these 2 tables. I can write a loop around all those so that I don't need to repeat the following codes for each range. Okay, so I want the font name to be Arial, their font size to be 9. I also want the text to be bold. We can assign a background color of blue with RGB of 00255. This is a rather famous code for a blue color. You can easily search and find the RGB code corresponding to the color you would like to have. I would also like to have the font color of this text to be white, and this is the color for white. Okay, and now we can also increase the column width so that the headers look nice. We could also apply, for example, wrap text and many other things, but it's good for now, I think. Another thing that can make this much nicer is to center align all the data we have here. So we can say output underline range, which we define it to be the first 3 columns of this workbook, API dot horizontal line, and we set it to be center. We apply the same to stats underline range, which was the range for our descriptive stats table. Let's run this cell. Now it looks much better indeed. Here, maybe for the title of statistics in here, we could in fact have another color and also make the column smaller to auto-fit the text. Okay, so this range was called stats underline name that range underline range, and let's try the background color with RGB of 153.76.0. And let's apply autofit to this range as well. Okay, now I hope you agree that looks better. Another thing here that is bothering is the number formats. If we have them with 2 decimals, they will look much better. So let's ask to show the numbers with 2 decimals in both the output data range and the stats data range. Okay, good. Maybe now I want to apply a background color to all these data range. Here I assign a RGB code for a gray color. The last formatting we would do here, and let's do it very quickly, is to change the borders for our data range. I would like to apply a white and thin border around the number cells. So again, I need to call API with borders. There I can pass the ID of the border. Each border has a specific ID, as you can see here. For example, border at the bottom of the page has the ID of 9, and the left border has the ID of 7, and so on. 5 and 6 are the borders I don't want to have here. Okay, so I can have a loop that goes through the border IDs from 7 to 13 and assign all those borders to white and thin. Thin is represented by number 2. Again, check the documentation in Microsoft web page for more details. We do the same for stat range as well. Now let's run it. Okay, that looks great to me. Again, you may be pickier than me and would like to spend more time on formatting. If so, of course, there's tons of other possibilities on formatting you can get deeper on by yourself. But in any case, I hope this was a good intro into formatting as well. I will hopefully prepare one video later on specifically related to this topic. Okay. At the end of our work, we can also save the book into a new Excel workbook and close these active Excel apps. This means that from now on, I can easily adjust the parameters for a simulation and run all these codes. It will go and open my Excel valuation model. It runs the simulations, save the plots and all the outcomes and descriptive stats, format them for me as I asked, save the outcome in the new workbook, and finally closes the apps for me while I am taking some breaks and having my coffee. Okay, that was it. I hope this was useful for you. I will be back soon with the next videos. Till then, I wish you wonderful days ahead.